everybody. It's my pleasure to welcome you on behalf of our Science student chapter. So today we have Dr. Sirani Perera from the Embry-Riddle Aeronautical University speaking to us about a fast algorithm for beam digitization. The floor is yours. Thanks again for agreeing to speak.
Thank you. Good afternoon, everybody. Thank you so much for inviting me to give a talk. And I thank the organizers in the Science student chapter inviting me to give this talk. And I take this opportunity to talk about a fast algorithm for beam digitization. And this was funded by the Faculty Innovation Research in Science and Technology grant in my university. And I thank my university supporting this research. And this was a joint work with my long-term collaborator, Dr. Arjuna Madanayaka, who is an electrical engineer in Florida, FIU, Florida International University. And then my amazing student, Levi Lynch, he will be starting his graduate studies in ETH Zurich. And let's start. So I'm going to talk a little bit background behind the structured matrices, and I'm going to tell why the structure is important in connection to the beam digitization transform. And once I speak about the beam digitization of the structures, and then we move on to the sparse and orthogonal factors for the new transform that we introduce. Once the factorization is introduced, we talk about the recursive and radix 2 algorithm for the new transform, beam digitization transform. And then we talk about the complexity results and then move on to the signal flow graph. Now, many problems in applied mathematics or the engineering cannot be solved by using standard techniques. But fortunately, one can look at the structure and use the structure to obtain beautiful solution in a time-efficient manner, or using the low complexity algorithm. Why the structure is important, again, come back to the low complexity algorithm, because we can derive the fast or the faster or the super fast algorithm. If we talk about the standard algorithm, for example, assume we are solving a system of equation where the coefficient matrix has no specific structure, and then you can use the standard Gaussian elimination like you guys learn in a linear algebra class or the numerical analysis class, and then you solve that system by using a n-cube operation. If you could utilize the structure and reduce the complexity a little down, we call those algorithms a fast algorithm because it's faster than the standard brute force calculation. If you could reduce a little further down, I would like to call it as a fast algorithm, not n squared, maybe n log n, like divide and conquer technique or the radix 2 algorithm. And if you could cut down the complexity more, or n log squared or n log n, n log cube n, those are called the super fast algorithm. There are a huge research group who's working on the structured matrices, and I thank all those amazing people who has been working in the structured matrix family, including my advisor Vadim Olszewski and his former advisor Thomas Kailath, and there are other researchers, Chandrasekaran, Gilbert Strang, and then Mark Van Barrel, and then Nicola, and then who else? And then Kailath, and I actually mentioned Kailath, and then Heinig and Rost, and all the amazing mathematicians who has been, and James Nagy, and there are amazing mathematicians who are working on the structured matrices. And I thank all of them, and Van Duren, and then also Nicholas Ham. When we talk about the stability or the error analysis, it is amazing. The field is amazing, and Wilkinson, and all these amazing people. And why these, and then Victor Pan. And why the structure or the fast algorithm is important, because once you reduce the structure, we can use that one to reduce the power consumption and cost associated with the integrated circuit. So it will open immense of applications in a digital signal processing. And when you talk about the structured matrices, there are two main families. One is called the moment type matrices, the other one called the recurrence type.
Can I ask a question?
Sure.
Could you back up one page?
Back up one page.
Yeah. But your super fast is actually slower than the faster.
I'm sorry?
The last column here, the last one here, the super fast actually is slower than the faster.
Yeah, that was something I was about to ask also, but I didn't want to bother. But to me, log n times log 3 is something which is bigger than n log of n.
Bigger than n log n.
No. Look at it. N log n mean n is replaced by log n. So it will be more faster. It will take less arithmetic operations. So look at this one. This is n log n. Your n is in this formula, this n is replaced by the log of n. So it's quite faster. If you just run n equals 2 to the power 2 t, and if you write the MATLAB code, you will see that the cost in computing this one is quite smaller than. Think about that. Log of n is like, if log of n is like this and n is like this. So it's once you think about that, this one is faster. It's required less operation comparing to n log n, because n is replaced by the log of n. That's what the symbol. Maybe you confuse with the symbol.
The square is a composition. So log
yes,
log
exactly.
Oh, okay,
yes.
I think that's what the source of the confusion was.
Maybe they confuse with that.
Ah, it's a composition.
Yes.
I see. Ah.
Yeah, it is a composition.
Oh, it's not multiplication. Is that what you mean?
It's
a composition, not a power. All right, so it makes sense now. Okay, all right. Okay, because the way it was formulated, I was not only willing to go forward with Yuan, but I was about to say objection, Your Honor, objection. I mean, no, no. Okay, so it's a composition. Thanks, Max.
It's a composition. Yes. Okay. So once you go down. So there are two types of structured matrices. One is the moment type matrices. The other one is recurrence type matrices. In the moment type matrices, we have Toplitz's and a Hankel matrix. These entries in these matrices can be described by specific moments. So the people, what you could see here, suppose in having n squared entries, you only need n parameters to determine this matrix and this matrix explicitly. So you don't need n squared operation. The famous algorithm, if you have a Toplitz's matrix as the coefficient matrix, if you solve that one by using famous fast algorithm, we call it as a Levinson algorithm, that can solve the Toplitz's system in n squared operation. There are much more algorithm later on appeared, and Victor Pan did some of nice work. And then he used the displacement structure and he factored these matrices, and he in fact obtained the inversion formula. There are wonderful formulas that are available for the Toplitz's matrices, and beautiful formulas to compute the sparse factorization of the Toplitz's matrix, and also to solve the Toplitz's system, and also the Hankel system, and also to obtain the inversion formula. These are called the moment type matrices. And then the matrix that you see in here is called the Bijousian matrix. That matrix is constructed by taking the coefficient of the polynomials. Recently, with my advisor, we derive a fast algorithm, which we use the structure of this matrix and the confederate matrix to compute the greatest common divisor of the two polynomial by using n squared operation opposed to n cube operation. And the other connection between the Bijousian matrix with the Toplitz's and Hankel, if you invert this matrix, those can be seen as the T Bijousian, which is the Toplitz's structure, or the H Bijousian, which is the Hankel structure that we have seen earlier in earlier page. The matrix that you see in here is called the H1 cosi-separable matrix. The matrix is said to be H1 cosi-separable when you talk about the lower diagonal, all the guys below the lower subdiagonals are 0, which is simply an upper Heisenberg matrix. And then if you block partition like that, if you take the 1, 2 block, it has a rank 1. Obviously, single row is rank 1. If you look at it, one row is a multiple of the other. So it's still rank 1. 1, 2 block has a rank 1. And 1, 2 block still has a rank 1. And obviously, one column, so it's rank 1. So you can use the generators to construct this matrix. What's the beauty in this matrix? Recently, it was found by Bella, Edelman, Goldberg, Olszewski, Eugene, that these co-separable matrices act as a superclass of the unitary Heisenberg matrix and a tridiagonal matrices. These tridiagonal matrices, if you take the characteristic polynomial of principal submatrices, those satisfy the 3 terms recurrence relation. And also the polynomial defined based on those 3 terms recurrence relation, which are orthogonal with respect to the inner product defined on the real line. And if you talk about the unitary Heisenberg matrices, if you take about the characteristic polynomial of the principal submatrices, those can satisfy 2 terms and also 3 terms recurrence relation. And then if you talk about those polynomials can also orthogonal with respect to the unit circle. So you can simply use the generators to construct these beautiful matrices, and we can use these generators to derive the fast or the low complexity algorithms. And then there are other matrices that lie somewhere in between the moment type and a recurrence type matrices. Such matrices called as a Vandermonde matrix. If you are in a numerical analysis class, you probably seen the subclass of the polynomial Vandermonde matrix, which we call as a classical Vandermonde matrix. When you are working with the interpolation problem, the coefficient matrix is simply the classical Vandermonde matrix. So this is a superclass of the classical Vandermonde matrix, which we call as a polynomial Vandermonde matrix, whereas R0, R1 up to Rn minus 1 are the polynomials with respect to degree 0 up to n minus 1, x1 up to xn are the roots of the degree n polynomial. What you could see here is the discrete Fourier transform, which can also seen as of having the Vandermonde structure. You might not see it with the polynomial Vandermonde matrix, but this has a structure similar to the classical Vandermonde matrix. And it's a Vandermonde type matrix, whereas the nodes that represent by the second column, these nodes are the primitive nth roots of unity. That's the discrete Fourier transform matrix, the DFT matrix. Okay. What we are going to talk about the beam digitization and how this structure can be utilized to derive the fast algorithm for the new transform that we're gonna introduce. So the reduction and minimization of the number of analog to digital converters is a paramount application in wireless communication, radar, microwave imaging, radio astronomy. If you talk about the 5G wireless communication, the system performance is primarily dependent on the signal to noise ratio because of the presence of additive white Gaussian noise from a variety of sources. And for the additive white Gaussian noise channel, so best possible compression of the signal can be achieved through the KLT, which is very well known. And then it was found by Britannic and Rao and Yip. This discrete cosine transform of type 2 is the closed form linear transform, and that is, it's a closed form linear transform, and which is very close to the optimal KLT. What we're going to do here, so we also know that, so once you have the DCT2 that can be used in array processing receivers for reducing the number of analog to digital converters in the system per time sample basis. once you have a per time sample basis, and we also notice that the endpoint discrete Fourier transform is applied to per time sample basis across the spatial domain, provide the orthogonal radio frequency beams with n log n complexity opposed to the n squared complexity. So what we're going to propose here, we propose the DCT compression and then inverse DCT decompression and subsequent DFT-based digital beamforming to achieve the reduced analog to digital converter channels or ADC channels. And in this process, we use the beam digitization transform as an intermediate step. So like I mentioned earlier, digital beamformers are popular due to their extensive usage in digital signal processing. So this beam digitization transform matrix, how we define by using the DFT and DCT, because we identify those are the closed forms. Okay, so how are we going to do that? Suppose you have an n point vector of the input, and then you hit with the DFT matrix to produce n beams, right? So once you have that, and then we realize that DCT2, which is a closed form for the KLT, which is used in decompression of the, compression of the signal. So then we realize, okay, DCT2 is invertible. So let us put that one in between the DFT and the input vector. Once you put that, the whole structure going to destroy. So we put the DCT2 inverse at the same time. The inverse of DCT2 is a DCT3. So you have different types. You might be wondered why I have been talking about the different types. There are different types, like a discrete cosine transform has 8 variants, and also same as the discrete sine transform that has 8 variants. These variants change based on the Dirichlet and Newman boundary conditions. That's why we have different variants. It was found that DCT3 is the inverse of the DCT2. Typically, instead of calling 2 and a 3, in electrical engineering family, they talk about DCT as DCT2, inverse DCT as DCT3. So we, like I said, you have an n input vector, you hit with the DFT to obtain n beams. So we realize that DCT2 is invertible. So you plug that one and it's inverse in between the DFT matrix and the input signal. And then we construct a new matrix, which we call as a beam digitization matrix. And what we are going to do is that's a new transform that you could see here. This is a new transform. And then we are trying to factor this one into the product of sparse and possibly orthogonal matrices. And this is the abbreviated version of the DFT matrix. And this is the DCT2 matrix. These are like n by n matrices. Okay, so before going into the sparse factorization, let's look at some historical remarks. FFT, fast Fourier transform, is the algorithm that's used to compute discrete Fourier transform and its inverse efficiently. Inverse of the discrete Fourier transform is a conjugate transpose because the beauty in that matrix, right? So in 1965, the FFT algorithm appeared to analyze the rotation of the helium-3 molecule. Since then till today, it's dramatically and significantly evolved in many areas like polynomial multiplication, solving PDEs, barcode analysis, fingerprint enhancement, image compression, so on and so forth. So among these, this is, it's also known that the Gauss is the one who first came up with the FFT algorithm around 80s. And then after that, Cooley-Turkey reinvented that algorithm. And then the Yauni, what she did was, she reduced the complexity count in here through scaling at the end. And very recently in MIT paper, they reduce the complexity a little further down, 6% of around 6% reduction of the complexity in Yauni's paper. And then they mentioned that, okay, this is the lowest arithmetic operations that you could obtain in computing the FFT algorithm for the DFT matrix. And they also use their algorithms to derive subsequent algorithm for the versions of the DCT, discrete cosine transform, and also discrete sine transform. From here onwards, we have a discrete cosine, or this one is a beautiful work done by Heidman. And in there, he gave an abstract notion for the DFT matrix to the polynomial rings. And from here onwards, you will see the application of the discrete, papers in connection to discrete cosine transform. Discrete cosine transform. And mainly, the discrete cosine transform and discrete sine transform are the real variants of the discrete Fourier transform. So once you identify these real variants, if you wanted to derive the fast algorithm, there are two main techniques that we could use. We could use the polynomial arithmetic technique or the matrix factorization technique. In polynomial arithmetic technique, what we do is we take the matrix DCT or DST, hit with the vector, we have an output. We take this output, construct the degree n polynomial, and then we use the divide and conquer technique to the degree of the polynomial to reduce into n by 2, n by 4, and n by 8, and so on and so forth. That will help us to derive the fast algorithm. Mauras, this paper used the polynomial arithmetic technique. And then these are matrix factorization. This is matrix factorization. These two are matrix factorization. And this is a matrix factorization. In a Strang paper, he's the one who first mentioned that the columns of the discrete cosine transform matrix 1 up to 4 are the eigenvectors of asymmetric second difference matrix, and hence the orthogonal. The later on, Britanek, Yip, and Rao, they used the same approach that was used by Gilbert Strang to prove the remaining discrete cosine transform, which is cosine transform of type 5 till type 8, and also the sine transform 1 up to 8. And they show the orthogonality based on the similar approach as in the Gilbert Strang paper. And then this paper, this use a different instruction, neither polynomial arithmetic technique, neither matrix factorization technique. In that paper, they use the polynomial division in the matrix form. That's very beautiful. So once they do that, there was an earlier paper of Olszewski and his former advisor. What they used was they took this transform and they said that these transforms can be seen as a product of the weight matrix and the Vandermonde matrix. So then this paper, they take that approach and then use the polynomial division in the matrix form, and they obtain the quotient and a remainder, and they convert it back into the matrix form, and they obtain a sparse factorization. But the thing is, most things are missing in this paper. What we did was, in our papers, we further developed sparse factorization. We factor those weight matrix into the product of sparse matrices, and we factor the Vandermonde matrix again into the product of sparse matrices, and we put those building blocks nicely, beautifully together to derive the lowest complexity DCT 1 up to 4 algorithm. And those are the lowest multiplication complexity DCT algorithm right now, as of available. These are one of my previous work with my collaborator. And then when we go back to the new transform again, and I mentioned that we identify the new transform through the DCT compression, inverse DCT decompression, and subsequent DFT-based digital beamforming to achieve the reduced analog to digital converter channels for N beams. So for that, in the intermediate calculation, we need this beam digitization transform matrix, which we construct by using the DFT, discrete Fourier transform, and a discrete cosine transform. And if you remember, this is what we had. Look at the cumbersome matrix that we had, but we were able to use a hybrid of polynomial multiplication techniques and a matrix factorization technique to express this one into the product of sparse matrices. And the nice thing about it, this transform or this sparse factorization runs recursively with the DFT factorization and also runs recursively with the DCT2 factorization. If I pointed out the DFT factorization in Cooley and Turkey paper, it has this one. I mean, this is without the scaling version. The scaling version came to the Yaunis algorithm. And then this is the DCT2 factorization, which I obtained. And then later on, I was able to design the integrated circuit or the signal flow graph connection to the integrated circuit, and also the technique to reduce the multiplicative complexity of the DCT circuitry. And that was the patent was awarded very recently. That was somewhere in January 26, 2021, I mean this year. So if you look, what's important in this algorithm, look at this algorithm and look at the algorithm in here. So this algorithm, earlier on, these transformations were depend on each other. That's what the researchers has been found. They rewrote or they obtained the factorization for DCT2 in terms of DCT4 or some other factorization. These different types depend on each other. Instead of interdependent transform, I propose the self-recursive transformation for the DCT2 using the sparse matrices. Look at how beautiful sparse these matrices. This is a bidiagonal matrix, whereas we only have one multiplication. Multiplication by one is not counted anyway. And then this is another sparse matrix, and this is a diagonal matrix, and you have n over 2 multiplication. This guy is the identity and anti-diagonal, guys. And this, if you could scale towards at the end, then we can get rid of the multiplication in here. And this is the half of the, twice the half of the itself. Permutation matrix does not cost anything. It's like you take the YS and you replug in a different order. So it's a nice, beautiful factorization. So the proposed new transform, which is a beam digitization transform, and then the corresponding algorithm can run recursively through the discrete Fourier transform and also the discrete cosine transform. This is the algorithm. Look at how nice, how simple, how easy to implement. You don't need pages and pages to write. So this is the sparse matrix. I get rid of the scaling factor through that so that it will reduce the multiplication complexity. Multiplication complexity is the crucial part. The complexity for the addition complexity is not that crucial though, because for multiplexers, because for the multiplication complexity, I will talk about that in a signal program. We need multiplexers. Multiplexers are quite expensive. Adders are very cheap, $1 or $2. So reducing the multiplication complexity is the key to succeed or design the integrated circuit with the reduction of cost and power consumption. Okay, so we get rid of that one. And then this one is I took the whole matrix as a W tilde because the top block is identity, the bottom block is W. So I took the whole matrix as W tilde, but still you have n over 2 multiplication in here. That's beautiful. And then the cosine of 2 was applied for that. And this is the bidiagonal matrix, whereas you only have one non-unit non-zero entry, which is square root 2. That's not expensive. And then this is the half of the original matrix, half of the original size, because this goes to n over 2. And then half of the original size, this is a discrete Fourier transform matrix. If we can scale towards at the end, we can get rid of the cost in there, I mean multiplication cost. And this is the matrix with the identity matrix and a diagonal matrix. So it's quite cheaper. If you will, I will show the explicit complexity further down. So this is the scale version of the FFT algorithm. So I scale it. So you don't have a scaling factor here. So I bring the scaling towards at the end. So you run through the scale FFT, and this one is similar to the Yauni's case. And then this is the beautiful DCT2 transform that I was able to obtain in one of the other paper, and also some reduced multiplicative circuitry to the pattern. And so this one is, I get rid of the scaling again, and then this is the diagonal matrix, and then it's self-recursive, it executes itself, and it's a bidiagonal and a permutation. So it's a scale version of that again to reduce the complexity. If I show you the binary tree, it will look like this. So I had the beam digitization transform matrix at the top, and then it split into the three main components. So I have the half of itself, and then the half of the DFT matrix, half of the DCT matrix. And then every time when I have that divided into the half of its size, and then half of the DFT matrix and half of the DCT matrix. And fortunately, we have the self-recursive algorithm for the DFT, and then we have the self-recursive algorithm for the DCT too. And then we can run recursively these algorithms. So each step cost only big O n operation. This is big O n. This is n over 2, n over 2, n over 2, which is still big O n. This is big O n. So if I run this algorithm for t times, the complexity is n times t, but t is the log base 2n. So the complexity in computing the beam digitization transform is n log n. If I compute the explicit complexity, these are the explicit counts that we have. So the one in here, how we obtain this one anyway, this is the number of addition required to compute the beam digitization transform matrix by the vector. This is the number of multiplication required to compute the beam digitization transform matrix by a vector. And here is a number of complex counts. So you have a complex input, and then you count the complex, how many complex counts, and then you have the complex input and you count the real counts. My student is really good at this one. And who is Levi? Who is in this? I think he has joined the talk too, right? So anyway, how did we obtain these formulas? If you go back in here, so cost of computing this algorithm is depend on cost of computing this. So if I look at the multiplication, no multiplication in here, here I have n over 2 multiplication. I know the cost of computing this algorithm, which is based on one of my previous papers. And then I know cost of computing this one, because this is a bidiagonal, I only have one multiplication. This is the half of the cost of computing original beam digitization transform matrix. And this one we already know because we use the scale version of it. And then this one is identity and a diagonal box. So that one is, since we know the structure, we know the cost of computing that. So we ended up with the first order linear difference equation. And then we solve the first order linear difference equation with respect to the initial condition. And we obtain these addition and a multiplication counts. And then when I go down, actually this legend has to be changed. I'm sorry, I apologize for that. This one has to be complex. This blue is complex. This purplish color has to be real. This legend has to be switched, and same as this legend need to be switched. I apologize for that. and say, look at that. What I wanted to mainly show that if I have a n log n, say all these are in the same parity. So all these algorithms required n log n operation opposed to n squared operation, because we have the DFT matrix and a DCT matrix by the vector. So that caused n squared operation. But instead of using that, we cut it down to n log n complexity. And then, okay, the last part of the talk is based on the signal flow graph. And then we did all this math, but we did not tell you how the signal need to be transformed. So in a signal flow graph for the FFT, there are two main types. One is the decimation in time. The other one is a decimation in frequency. So decimation in frequency, your input signals are in the order, output signal are in the bit reverse, or whatever, based on the permutation in the order. And the decimation in time, input signals are in the bit, whatever the order, scramble, the output signals are in the order. So the nice thing about this decimation in time and decimation in frequency, if you know how to draw the signal flow graph in one domain, you can draw the signal flow graph in the other domain, which is simply the reverse of the flow design. When you construct this signal flow graph, there are main building blocks. The main building blocks are adders, and that reflect the addition. So signal coming in one direction and signal coming in the other direction, they both get together and they goes as a one signal. Or the gain, so signal coming in one direction and then there is a multiplier, and then with that, now the signal passes through. Or the splitter, signal coming in one direction and it goes to the different direction. Those are splitters. These are the main building blocks in the signal flow graph. And then here is the signal flow graph for the beam digitization transform for 8-point input. If you have an 8-point input, these are my 8-point input, these are my 8-point outputs. Say, look at this. You have a nice, beautiful butterfly structure that we usually see in FFT types algorithm. And these are the weights or the gains, which are corresponding to the multipliers. And these are the blocks. These blocks, you have a DCT. You remember that I mentioned that this algorithm, this is a half of the original size, because I said this is the beam digitization transform of size of 8 input case. So this is the beam digitization transform of the 4 input case. These are the DFT matrix, and this is the DCT2 matrix. And then if I go to the next slide, you will have those precise precise signal flow graph in here in each block. This is the beam digitization transform for 4 input, and this is the discrete Fourier transform for 4 input, and this is the DCT2 for 4 input. Look at this. All these red guys, all these guys are multipliers for the multiplexers. If I go that, see, look at how many multiplexers that we have. These multiplexers, think about it, right? We had a matrix, this beam digitization transform matrix, and that we have seen earlier. And then if you have a matrix, it's a full matrix. And we had this full crazy matrix in terms of the cosine and then the primitive roots of unity, and we factored into product of nice, beautiful sparse matrices. And if you take that matrix, if you hit with a vector, right, matrix vector product, if you have n by n matrix, hit with the vector n by 1, you need say in each row by column, you have a n multiplication, n minus 1 addition. If you go up to n step, you have n squared multiplication and n times n minus 1 addition, n squared multiplication. Imagine, so if I have 8 input, I need 64 multiplexers. Instead of 64 multipliers, how many I have? See, 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Almost we cut down the complexity by 74%. So that means we reduce the complexity or the power consumption and chip area drastically. That will help us to, it's simply It cost like, imagine it's like a 70% cut down. It's a drastic reduction. And this signal flow graph, if you give the signal flow graph, if you ask my student and give the factorization, he will draw the signal flow graph in 1 hour. He's that good in signal flow graph, and I thank him. So anyway, so these signal flow graphs are amazing. So that, what does it tell? It drastically cut down the complexity. And then what we have seen in here is we obtain the fast algorithm n log n opposed to n squared, and it's run recursively with the FFT algorithm and DCT2 algorithm. And then we have the radix 2, problem of size n divided by problem of size n over 2, and then problem of size n over 4, and n over 8 goes like that. And then this beam digitization transform matrix is the hub or the centerpiece in the process of the reduction of analog to digital converter channels. We had in this talk, we have a beam digitization transform matrix, and then we had to combine that one with the DCT3, and then this whole process can subsequently reduce the analog to digital converters in a digital signal processing. And then these can be used to customize or design the integrated circuit, and can be used in a very large VLSI architecture, very large scale integration architecture. And that's simply it. And thank you so much again inviting me to give a talk in your student chapter. And I also thank my wonderful collaborators again and my university. Thank you again. Any question?
All right, guys, let's thank our speaker one more time. Thank you so much for this wonderful presentation.
Thank you.
At this point, we open the floor for questions. Does anyone have any questions? Well, I have a question.
Sure.
Which software did you use to implement your algorithm?
We use MATLAB, and we also use C. And we can, once we have a MATLAB code, we can use easily put it in Python, and we put it in Python as well. And that we did very recently for some other purpose, because we're going to use some of these results to obtain some other results.
Okay, so what do you use mainly? Do you use MATLAB or Python?
Mainly it's a matrix, right? Matrix language, MATLAB. And then once we have the MATLAB code, we write the Python code and a C code. And in fact, Levi, he started to typically we check this signal flow graph when the input signals are gone, and then we have to double check, even though we draw this signal flow graph, we have to check, the signal passes through each and every, every line, right? We have to check whether once it passes through these blocks, with all these blocks, you have to check whether it's nicely, beautifully synchronized, and whether it's matched exactly with this matrix vector product. And we usually use MATLAB for that, but Levi, he started to work on the C to check this signal flow graph as well. That's amazing. Yeah.
Okay, thank you. And also, do you have the steps for your algorithms written down, like step 1, step 2, step 3? In your paper, or is it just a generalized version?
No. In this one we didn't publish it. This is our recent work, actually.
Okay.
This is very recent work, and this results we didn't publish yet, because we have some other papers lined up. We wanted to send that away, and then we're gonna sit and write this one in this summer. And then, but we have algorithms written for the discrete cosine transform step by step, algorithms written in there. And then we have some other work that we did recently in connection to the beam forming, multi-beam beam forming. Those are written, algorithms are explicitly written in the paper, yes. But this one we obtain everything, and everything done, we have to sit and write that one, because we have some other works to finish up first. We finished up, other papers that has nothing to do with this one anyway. So once it is done, we're gonna shoot this paper out.
Thank you very much for answering my question.
Yeah.
Does anyone else has any other questions for the speaker? Okay, let's thank the speaker one more time. Thank you so much